Ever feel like, I don't know, we're kind of missing a part of the puzzle when it comes to the universe? I mean, like, we've learned a lot about the cosmos, but there are still these big mysteries, right?
Yeah, definitely
Like,
is.
what is dark matter? That's a big one.
Huge.
And what about all that antimatter that's supposed to be out there? Where'd it go?
Yeah, those are some of the biggest head scratchers in physics right now. The
Oh,
kind of things that keep you up at night.
for sure. And that's what makes this whole deep dive so interesting, at least to me. We're going to be looking at axion-like particles.
And ALPs.
Yeah, ALPs for short.
Catchy, right.
Right. So basically, you can think of these ALPs as, well, they're hypothetical particles.
Hypothetical, meaning we haven't actually found them yet.
Right, exactly. But they could, like, help us solve some of these cosmic mysteries we were talking about.
Exactly. They might be the missing piece of the puzzle.
Okay, so we're on a detective mission here, and we've got some clues to sift through, right?
We do.
We're looking at this paper. It's called Probing MeV to 90 GeV axion-like particles with LEP and LHC.
It's a mouthful, I know.
It's a mouthful, but honestly, the paper itself, it's actually pretty fascinating. Don't let the title scare you. It's full of twists and turns, you know.
It's a real page turner. Okay, not really, but
Not really, but you get it. Anyway, this deep dive is all about how scientists are using these massive machines, these particle colliders, to try and track down these sneaky ALPs.
yeah, these colliders are pretty amazing.
We're talking about the Large Electron-Positron Collider, or LEP, and then its more powerful successor, the Large Hadron Collider, or you guessed it, LHC.
And these machines are incredible. We're talking smashing particles together at almost the speed of light.
Okay, yeah. That does sound pretty impressive. But why go to all that trouble? What's the big deal about these ALPs anyway?
Well, you see, our current best understanding of how particles work, we call it the Standard Model, it does a really good job. I mean, it explains a lot of things.
Okay.
But, and there's always a but, right? There's some things that just can't explain.
Like dark matter, for example.
Exactly. Dark matter being a big one.
Okay, so the Standard Model, it's like a really good map, but with some blank spots.
Yeah, that's a great way to put it.
And the ALPs might be what fills in those blanks.
You got it.
Okay. But if they're so hard to find, I mean, how do we even start looking for these things?
Well, that's where it gets really clever. This paper, it focuses on using data from LEP.
LEP, the first collider we were talking about.
Here's the one. It was decommissioned back in 2000. But even though it's gone, the data it collected is still incredibly valuable.
Wow. So we're talking like archival data.
Exactly. And what they were looking at, these researchers, they were particularly interested in how this one fundamental particle, called the Z boson, decays.
Z boson, okay. And it decays. What does that even mean?
So these Z bosons, they're kind of like, I don't know, imagine them as little firecrackers.
Mm-hmm.
And when they go off, they explode into other particles.
Okay, I'm with you.
Now, the theory is if ALPs exist, they could actually mess with how those firecrackers explode. They could change the pattern of the particles that come flying out.
Interesting. So by looking at how these Z bosons decay, we could, what, find evidence of ALPs even if we can't see them directly.
Exactly. It's all about looking for those subtle hints, those indirect signals.
Sneaky. I like it. So what were they looking for specifically in those Z boson decays, I mean?
So they were looking at cases where the Z boson decays into photons.
Photons, like light particles.
Light particles, exactly.
Wow. Okay, so they were looking for Z bosons turning into light, essentially, and somehow that's going to tell us about these ALPs.
You're getting it?
Yeah.
They were analyzing how often these Z bosons decayed into 2 photons versus 3 photons.
2 versus 3. Okay, why is that important?
That's the million-dollar question, and that's what we'll get into next. Because here's where things get really interesting. And it all has to do with this sensitivity gap in our ability to detect ALPs. We can see them if they're heavy enough, but there's this range of masses where they're just too light to spot directly.
Too light. So how are we supposed to find them if they're hiding in plain sight?
Well, that's where this LEP data comes in, and it's pretty amazing, actually. Turns out they might have already given us some clues. It's kind of like, all right, imagine you've got this scale, right? But it's kind of a weird scale.
Yeah.
It can only measure things above a certain weight. Anything lighter than that, and it's like, nope, nothing to see here.
So you're saying there are ALPs out there, but they might be too light for us to even notice them with our current tech.
That's the idea, yeah.
Yeah.
Like trying to weigh a feather on a bathroom scale, the scale's not sensitive enough.
Okay, that makes sense. But then how did they figure out this sensitivity gap even exists? If the detectors can't see these super light ALPs...
Well, even though the ALPs themselves might be too light to be detected directly, they still have to obey the laws of physics, right? I mean, they still have energy and they still have momentum.
Right. Energy and momentum, those are kind of important.
Absolutely. And that's the key here. Even if we can't see the ALP itself, we can look for what it leaves behind. Like imagine you're walking on a beach and it starts to snow.
Snowing on the beach. Okay, that's an interesting image.
You see footprints in the sand, right?
Yeah.
But the snowflakes themselves, they melt away. So you're left with these traces, these hints of something that was there, even though you can't see the snowflakes anymore.
So the ALPs are like the snowflakes, and their footprints are.
The footprints are the energy and momentum they leave behind. And in this case, the footprints are in the form of photons.
Photons, again with the photons. So how did that help us find the ALPs?
Okay, so here's where it gets really cool. When an ALP decays, it usually decays into 2 photons.
Okay.
Now, if those photons are really, really close together, like really close, they might hit the detector at almost the same time. And guess what?
What?
The detector might think it's just 1 photon instead of 2.
Oh, wow. So it's like those optical illusions where you think you see one thing, but it's 2.
Exactly. Except in this case, it's not our eyes being tricked, it's the particle detector.
So we might have all this data from LEP, from those Z boson decays we were talking about, and it might actually have some of these hidden ALPs in there masquerading as single photons.
That's the idea. And because LEP ran for years, they collected a ton of data on Z bosons decaying into 2 photons. That's the normal decay that they were looking for in the first place.
Right.
But now researchers are going back and looking at that data again, but with fresh eyes, you could say. They're looking for those cases where what looked like a single photon might actually have been 2 photons from a very light ALP decay.
That's incredible. It's like they're uncovering a secret code hidden in data that's been sitting around for decades.
I know, right? It's amazing. And it gets even better.
Better. How?
Remember LHC?
The big kahuna. How could I forget?
That's the one. So LHC, it's smashing protons together instead of electrons and positrons like LEP did.
Right. Protons, those are bigger.
Way bigger. And that means more energy. And more energy
More
means...
possibilities.
You got it. More energy means we can create heavier particles, explore higher energy scales, potentially see things that LEP could only dream of.
So LHC is like the ultimate particle hunting machine.
It's pretty close. I mean, it's a truly incredible feat of engineering.
So to be clear, LHC can help in this ALP hunt in 2 ways, right? First, it can just produce more Z bosons, so we have more chances to catch those rare decays where ALPs might pop up. And second, it might be able to directly create heavier ALPs, the ones that are too heavy for LEP to produce.
You've got it. More data, higher energies. It's like upgrading your detective kit with all the latest gadgets.
I love it. But even with all of this, it still sounds like finding these ALPs is no walk in the park. I mean, you're talking about looking for incredibly rare events, right? It's got to be like finding a needle in a haystack.
You think finding a needle in a haystack is hard. Try finding a specific grain of sand on a beach. That's more like it.
Okay, point taken. So how do they do it? How do physicists even begin to sift through all that data, looking for these almost invisible events? It's amazing how even with these incredible machines and the brains behind them, it's still so hard to find these tiny particles.
It really shows you how we're really pushing the limits here. You know?
Yeah.
I mean, think about it. These particles, they barely interact with anything else.
Yeah.
It's like trying to find, I don't know, a specific snowflake in a blizzard.
Okay, yeah, that's a good one.
And then there's a sandstorm happening at the same time.
Okay, now that's just crazy.
That's what we're dealing with here.
So how do you even start? I mean, how do physicists even tackle that? Finding these almost invisible particles in all that data.
Well, they've got to get creative, that's for sure. They're using, like, really sophisticated algorithms. And they're using machine learning, too, all to help sort through the data.
Machine learning, huh? So they're basically training computers to become, like, super particle hunters.
That's the idea. These computers, they can spot those really subtle clues, the kind of things that humans might miss. And they're getting better all the time, these techniques.
So it's a constant race then?
Always. Trying to stay one step ahead of these sneaky particles. But, you know, it's not just about finding the ALPs themselves. There's a bigger picture here, too.
Oh, okay, I'm listening. What's the bigger picture?
It's about what finding them would tell us about the universe. Because the energy levels where these ALPs might be hiding, that could be the key to a whole new understanding of physics.
Energy levels. Now you're going to make me ask you to back up a little. What are energy levels in this context?
Okay, so think of it like this. The universe, it plays by a certain set of rules, right? The laws of physics.
Right.
But those rules, they might be different at different energy levels. Like imagine a video game.
Okay, I like video games. Go on.
You need a certain amount of energy, right, to unlock new levels with new rules.
Yeah, to get to the cool stuff.
Exactly. And the universe might be kind of similar. These different energy levels could be like hidden levels in the universe with their own unique set of rules.
Okay, that's kind of blowing my mind a little.
And that's the thing about these ALPs. If we find them, and if they're at these specific energy levels, it could be like unlocking one of those hidden levels.
We could be looking at totally new forces, right?
Right. New dimensions, maybe. Even new symmetries in nature. Things that our current understanding of physics just doesn't cover.
It's not just adding a new particle to the list, it's like rewriting the textbooks.
Exactly. And even though the odds of finding them are, well, they're not great.
They're still looking.
We're still looking
Right.
because it's just too tantalizing to resist. It's like this is our drive, to unravel these big mysteries of the universe.
It's a pretty amazing thing to be a part of, wouldn't you say? Even just as observers. Well, that brings us to the end of our deep dive into the world of ALPs, from those giant particle colliders to the incredible work that physicists are doing to analyze all that data. I don't know about you, but my brain is definitely buzzing right now. So keep exploring, keep those questions coming, and never underestimate the power of human curiosity. You never know what we might discover next.